Okay. And I should also say, if people have questions and they want to put them in the chat, you could do that too. And then, whoever is chairing can bring that to the attention of the speaker if need be, or other people can answer the questions. Okay, so we have now a talk by Jiacheng, who's a graduate student, I think, at Princeton on superposition principle and mimicking theorems.
Thank you. Hi, everyone. Thank you for. Can you hear me? Yeah. Okay. Yeah. Thank you, everyone, and thank you for inviting me here. So today I'm going to talk about the superposition principle and its application, the mimicking theorem. This is a joint work with my PhD advisor, Misha and Dan. Okay, so first the outline. The outline is pretty straightforward. So basically, I will first speak about the superposition principle without the common noise, which is a previous result by Figali and Trevisan. And the second part would be our superposition principle with this common noise, part. And at the third part, we will talk about how to use this superposition principle to prove a so-called mimicking theorem. Okay, so for the first part, the superposition principle without the common noise. So the starting point is, let's consider a very standard SDE here, where this xt is a process satisfying dxt equal to some drift b xtt and some diffusion process sigma xtt. And a very well-known result is by this Fokker-Planck equation, we know that the density function of this xt, which is rho t, should admit the following PDE here. So this is a parabolic PDE here, and this can be easily obtained by the Ito's formula. And so basically this Fokker-Planck equation gives one direction from this SDE problem to this PDE problem here. So a natural question is, how about the other way around, in the sense that if we are given some PDE problem, can we somehow generate this SDE process here? So the answer is yes, and some well-known result is from Figali and Trevisan, in the sense that suppose we have a density function rho satisfying this following PDE problem here, and we have some integrable condition, then we should be able to find or to construct some SDE satisfying this. Basically, we'll have a standard SDE here, satisfying the drift being this b of xtt and the diffusion being this sigma xtt here. The key point here is that this b and sigma, we actually don't need too much regularity assumption here. We only need some integral condition. Basically, we don't need any smoothness condition for b and sigma. And so some interpretation here is that, so this direction basically gives a stronger connection between this SDE problem here and the PDE problem here. So in the sense that if we have existence and uniqueness for this SDE, this will induce some existence and uniqueness for the PDE, and vice versa. Basically, we have some existence and uniqueness for this PDE part, then we should have some well-possessed existence for this SDE. And also there is some applications here, which we will discuss later, basically by we can use the superposition principle to prove some mimicking theorem. And we will discuss that at the last part of the talk. So this was some previous results, basically for a very standard SDE, which only have. Yes.
Can you clarify what you mean by solution? You mean weak solution?
Oh yeah, weak solution.
Okay.
Yeah, thank you for the clarification. Yeah, there is a weak solution for this SDE here.
No,
and,
the PDE. I mean, you.
Oh, the PDE.
Smoothness, and then you take derivatives. So you must mean something.
Yeah, indeed. This for both the PDE and the SDE, they are both weak solution.
Okay.
Thank you for the clarification. And so the next part is the main result for our talk. So basically, we will consider some superposition principle with the common noise. And by meaning of the common noise, we were looking at McKean-Vlasov type SDE with the common noise and this conditional distribution here, in the sense that we are looking at some process xt, where the drift part is b of xt mu tt, And the diffusion part, we will split it into two parts, where the first part is driven by this Brownian motion dWt, and then the next part is driven by some other Brownian motion dBt. We assume W and B being independent Brownian motion, and the mu t here is the law of the xt, is the conditional law of the xt given this B, given this Bs part, given the second Brownian motion Bt here. And usually we call this Bt being some common noise. And the reason we call it this common noise is because such SDE usually shows up in the like mean field game and control problems with the common noise. And also it shows up in some dynamics of particle in large scale limits of a particle system with mean field interaction and common noise here. So the McKean-Vlasov type shows up because the drift and the diffusion all depending on the law, and also it's depending on the conditional law. So we'll do some similar arguments as we did before. Basically, we first, to simplify this problem, we only consider like the constant coefficient case. But in general, we'll have a more general result where we assume this coefficient. We assume in the coefficient is in the diffusion, the coefficient also depend on this xt and mu t. So, but to simplify here, we only assume that the drift part is depending on xt and mu t. So we can similarly write some stochastic Fokker-Planck equation for this mu t, in a sense that, so basically this the term here is just using Ito's formula and then take expectation. We should be able to write some evolution of this mu. So this is deduced by the Ito's formula, and the key point here is this mu t here. To compare with the rho t before, this mu t is still stochastic, and this SDE and this somehow SPD here, since there's some stochastic term here, this will provide some connection, at least provide this connection from the SDE to this SPD here. This will provide the connection between this xt and mu t. Or in other words, if we are given the law of the whole process here, we should be able to use Ito's formula to get the evolution of the marginal law. So this was the first step. And since we are working with the common noise here, so this will not be the only step we have, since for this part is still stochastic. So we will do another step. Basically, let's denote this pt as the law of this mu t here. And we will somehow try to determine the evolution or the equation for this pt here. So to have this equation, we will have some test function phi I and some f, and we somehow need to write the dynamics for this test function f over this mu t and phi 1 all the way to mu t of phi k. So this would be the evolution equation for this ps. And as long as we can take all the test function phi, and for all k and for all f, we can write this similar equation here. And this equation should be able to derive the evolution for this, the law of the mu t. And this formula, even though it's a little bit nasty, but still it can be easily deduced by the Ito's formula. And similarly, this will give us this connection between the mu t and pt. Basically, as long as we know that the mu t satisfies the previous SPD here, we should be able to know by Ito's formula, the law of the mu t should satisfy this equation, and we call it, we can still call it some Fokker-Planck equation. But in here, so basically this is a Fokker-Planck equation for some distribution, so we can somehow understand it in terms of some infinite dimensional PDE here. So this was the first direction, basically from xt to mu t and then to pt. So our superposition principle, as we had before, is more like this, the reverse direction here. So our main result is basically assume this pt satisfy the previous PDE, and also we have some integrable condition here. Then we should be able to construct some mu t and xt satisfying this SDE. And also we have this mu t being the law of the xt here. And again, our thing here is the weak solution. So basically the superposition principle provide us an reverse direction, in the sense that we starting with the PDE for this PT here, and then we can use this PT to construct some mu t, and then we can construct some PT, some xt here. So to summarize here, we have this connection of the following three terms. First, this xt which satisfies some SDE, and this mu t satisfies a stochastic Fokker-Planck equation, which is the stochastic PDE here. And then for the PT, we have some PDE. So the Ito's formula or the Fokker-Planck equation provide us some direction from xt to mu t to PT. And in the other direction, the superposition principle provide us the reverse direction in the sense that we, starting from this PT, we can construct some mu t and then construct some PT here, construct some xt here. Yeah, so this is our main result here, and yeah, due to the time, I will not explain some like the proof details here, but I just want to mention this PT to mu t is more like the previous superposition principle, but we somehow needed to apply it on the R infinity space. And for mu t to xt, the difficult part should be we have some stochastic term here, and we will need some stable convergence argument to provide some superposition principle from this mu t to xt. And for the last part, we will need let's introduce some application which using the superposition principle. So again, start with some mimicking theorem without the common noise, in the sense that if we consider this SDE here with some general drift BT and sigma t, then there exists some B hat and sigma hat which can be taken achieved by taking conditional expectation, and then we can have some weak solution of this SDE such that they have the same marginal distribution, but in this case, this drift and the diffusion are just some function of t and xt. So the proof of this mimicking theorem can be obtained by the superposition principle. The reason is that by Ito's formula, we can just write out the evolution equation for the density for this xt here. And this is just by Ito's formula, and then using Tower rule, we can like replace this BS by the conditional expectation of BS. And this equation actually falls into the Fokker-Planck equation. Then by the superposition principle, we can construct another x hat and w hat such that they have the same marginal distribution, since they are both the this marginal distribution solves this equation here, and also this x hat should have some very nice drift and diffusion in the sense that it's just some function of xs and t. And this mimicking theorem with the common noise will use the similar procedure, so we'll not explain it in detail, but we will just have this statement here. So again, if we consider this SDE, where we have a general BT here, and we have to simplify this problem, we just have some constant sigma and gamma, and this mu t being the conditional law of xt here. Then we can still construct some b hat, in the sense that this b hat is some conditional expectation given xt and given the mu t here. Then we should be able to construct some weak solution, in the sense that this drift term is only some function of xt and mu t. And the important thing is that in the end, we have these two SDE, and these two SDE will share the same marginal distribution, both in X and in mu. So this would be the mimicking theorem with the common noise here. So the point is we keep the marginal distribution while localization the drift. And also some application would be in the mean field control problem. This will help proving some optimal Markovian control. And that's it for today's talk. Thank you.
All right, thank you very much, Jiacheng. We have a minute if anyone has a quick question that they want to. Okay. No, we can always, there'll be a break after the next talk for a few minutes. Always ask more then.